Hello, y'all. Darrell Berry Jr. here, back for some STEM. As promised, we'll look into the Fourier that we left off on last week. We'll actually go straight to the textbook and read what it has to say on that matter. If you recall, last week, we started with, there we go. Remember last week, we started with at least we finished with the infinite square wall solving for the wave equation. We went through these components here, it being even and odd, how the node is one less than the state. We went through the orthogonality, and we left off on this last point. It describes it as being very complete, and it talks about the Fourier. So we'll actually read that part and go into that. And be sure to like, subscribe if you haven't already. Help me get to 1,000 subscribers. And we'll go ahead and get started. This one should be a brief one. We'll go through this section here and discuss what it's talking about. This is Griffiths, quantum, and this is section 2.2. And the number 4 on the points, which is talking about the wave functions here. It promised a time-independent Schrödinger equation has delivered an infinite set of solutions, one for each positive integer. And that's because from before we solved for psi, and we got this psi here, where n is a positive integer. But that's what it's talking about here. The psi is all of these things. We can have psi 1, psi 2, psi 3, and so forth. I'll put an n there. The first few of these are plotted in figure 2.2. So it's talking about this figure here, which we looked at last week, how the first state is n-1 for the nodes, 0 nodes, the n's don't count. 1 node for state 2, 2 nodes for state 3. They look just like standing waves on the string of length A. That's the strength is length A, which carries, and psi 1 carries the lowest energy. It's called the ground state. The others of increased proportion to n are called excited states. And we'll look at the fourth property of these that we left off on last week. It says they are complete, these psi wave functions, in the sense that any other function, f of x, can be expressed as a linear combination of them. So f of x is some function, let's say, for example, some kind of polynomial, like x to the n plus x to the plus ax to the m plus bx to the o. And, this function can be expressed as some sum, infinite sum, of these psi's that we found in the first part with a coefficient in front. So plugging in the psi that we saw for last week, so look at the video last week to see the solution to how we got this. I'm not about to prove the completeness of the functions. Curl 2 over a sine n pi x over a. But if you've studied advanced calculus, you will recognize that equation 2.35 is nothing but the Fourier series for f of x. And in fact, that any quote function can be expanded in this way is sometimes called the Darrell-X theorem. Let's see what this is. See, for example, Mary Boyer's mathematical methods in the physical sciences 3rd edition. F of x can even have a finite number of finite discontinuities. So maybe we'll look at this next week. I believe I have this book. maybe the one for next week, we'll take a look at page 356 and talk about that. We'll keep going with this for now. The coefficient Cn can be evaluated for a given f of x by a method I call Fourier's trick. And they're talking about this coefficient here to make this psi work for any given function. So there needs to be a coefficient in front of each psi to make it all work out. We have to find the coefficient. So the coefficient Cn can be evaluated for a given f of x by a method I call Fourier's trick, which beautifully exploits the orthonormality of psi of n. Multiply each sides of equation 2.35 by psi m x asterisk and integrate. So basically what we're doing is we're taking this equation here and we're multiplying each side by the complex conjugate of a different coefficient. Again, this is just the psi that we solved last week. Now, the reason why this works the way it does is because, if you recall, we discussed last week that the orthogonality were only where these are the same, where n and m are the same, do we get a value, otherwise we get 0. So this will allow us to extract out something. Let's keep on going with this. So now we're going to integrate. And now we have, make sure to make another line somewhere. Let me just move things around a bit. So basically this summation is summing the C and summing the psi as well. It looks like we could just bring that out. Now, we'll put this like this. Recognize this. That's just psi. If we scroll back up here, we can see that psi is square root of 2 over a sine of n pi x over a. And that's psi x. So that means that we can fill that in as such. So this is what we have here. Now, if you recall also from last week, this is the Kronecker delta. And welcome who joined. Be sure to drop a line. What I was talking about before. So this is basically the Kronecker delta, where it's going to equal 1 if m equals n, and 0 if m equals not n, which means we'll only get a value when they're equal. So we can say this equals sum n equals 1 infinity Cn Kronecker delta mn, and we can say Cn1, where m equals n, and that's why the book has Cm, because m equals n, otherwise we won't have a value. So now we've caught up, those are all the steps in between the line right there. This is basically what they did here. Notice how the Kronecker delta Q is every term in the sum except for the one where n equals m. Thus, the nth coefficient in the expansion of f of x is now, in this case, we utilized m and got m. So we want n. We do the same thing, but instead we multiply with the n psi. Now, one of the things that seemed confusing to me is if you look at this, f of x has c of n, but then we solve c of n with f of x. It seems kind of circular. And this is what I mentioned last week, how when we utilize this f of x, we have to utilize the finite form of f of x. So it actually becomes more clear in this example here, where f of x is this psi. So that's the psi that we plug in right here. Where is it? Here. So you notice that they normalized it, but then we plugged in f of x in finite form here. Let's see my mouse, yes. And then we're able to solve for the Cn. So it seems a bit strange, a bit odd. At least to me it did. All right, so there we go. I did a few extra steps. Okay, so we left off here. So now we have 2.37. How we get C of n, we have to use the finite form of f of x. These four properties are extremely powerful, and they are not peculiar to the infinite square world. The first is true whenever the potential itself is a symmetric function, and the first is even and odd. Psi 1 is even, psi 2 is odd. So ironically, it's the opposite of the number psi 1, odd number, even, psi 2, even number. The function is odd. It's like how the node is always one less than what it was. The second is universal, regardless of the shape of the potential. So the second is as you go up in state, the node is one less. Orthogonality, the third one, is also quite general. It shows you, I'll show you the proof in chapter 3. Completeness holds for all the potentials you're likely to encounter, but the proofs tend to be nasty and laborious. I'm afraid most physicists simply assume completeness and hope for the best. So apparently we assume completeness is usually, it can be assumed because it's often enough. So this seems like it's saying to me. In stationary states, equation 2.18 of the infinite square world, or so if we look at this, we check our psi. That's psi for the infinite square world. And all we have to do to make this the full time independent psi is take psi of x and multiply it by the t component. And I believe we touched upon this last week, is let me scroll up and make sure I write the default one properly. Here it is here. The default one is this, is EIT, to write it a different way, negative I, EN. t over h bar, and en, which we solved last week, is, recall, n squared pi squared h bar squared over 2m a squared. When we plug this in, equals negative I n squared pi squared h bar over 2m a squared. And that's what they have there. So we also plug this in all together. We have that big psi equals square root of 2 over a sine n pi x over a, and e negative I, to write it in the same form they have, n squared pi squared h bar over 2m a squared. I forgot my t. All right. So now we're able to make the full psi. I claim in equation 2.17 that the most general solution to the time-dependent Schrödinger equation is a linear combination of stationary states. So this is basically one of them as an n. What they're saying is if we want to get the most general one, we would add up all of these different psi, capital psi with n. And what I'll do to simplify the writing, well, n equals 1, we have that. We have our coefficient. And if you notice, it's the psi of x and psi of t. So not write all of those over. So, and we still have the same coefficient c that works with psi on its own, which we can solve the same way. If you doubt that this is a solution, by all means check it. It remains only for me to demonstrate that I can fit any prescribed initial wave function, psi x0, appropriate choice of coefficient Cn. The completeness of psi is confirmed in this case by the direct theorem, guarantees that I could always express psi 0 in this way, and their orthonormality licenses the use of Fourier's trick to determine the actual coefficients. So if we look at this, instead of using, I'm going to copy 237 down, and we'll look at this for a moment. And again, this is 237 from here that we worked out earlier. So what I'll do is fill some of this in. We have that. And in this case, f of x is going to be the time dependent psi at t equals 0. So we're just going to plug that in. They brought this out of the integral. And basically, this is the same thing we did before. We did Fourier's trick on both sides. We know we do the integral on this side. Orthogonality leaves us with just Cn. So we multiply with the Cn complex conjugate. I'll extract the n, so we'll multiply with the n complex conjugate. I'll extract the NCN. given the function that we're working with. And we notice as well, this big psi here, if we put t equals 0 for this, we end up with just psi. So therefore, psi x of 0 is the same thing as little psi in x. So sometimes I wonder why they utilize so many different terminologies or notations for the same thing. It used to be confusing. Maybe it is still confusing for you at the moment, but I've seen it before, so it makes it a little bit more understandable. But they call them the same thing by so many different terms. I wonder if it'd be easier to keep the same term, but I don't know. That's just the way it is. I just got to get used to it. That does it. Given the initial wave function psi x at t equals 0, which again gives us just psi n. We first compute the expansion coefficient Cn using the equation 2.40. And they call in this 2.40. And then plug these into equation 2.39. We get the general function. This is 2.39 here. So I obtain psi x of t. This is a general function in summation. Armed with the wave function, we're in a position to compute any dynamical quantities of interest using the procedures in chapter 1. And this same ritual applies to any potential. The only things that change are the functional forms of the size and the equation for the allowed energies. All right, so that seems like a good place to stop. As promised, we went into the Fourier method of solving for the coefficient to allow us to generalize these psi's as a sum to produce any function. And we could utilize this procedure, given that we solve for C of n, to end up getting any general wave function for the time-dependent psi. And then we can solve for any dynamical quantity, which I'm sure we'll end up getting into position and momentum and things like that, energy, and so on and so forth. So thank you all for watching. Those who popped in, if any questions comes up, be sure to drop a question or comment in the comments of the video. I'll see you all next week. We'll probably pull up that mathematical methods book and continue where we left off here. You have a good evening. I'll see you all next week.